The book starts this section with a technical note about linear approximations. In the last chapter, we talked about approximating single variable functions with lines, but we didn't look at any of the details of it. It turns out that this only makes sense if the function itself looks like a line near our approximation. A classic example of a function that isn't locally linear is the absolute value function at x equals 0. No matter how much you zoom in, you will never eliminate the corner, and so it will never look like a line. There is a similar condition for functions of two variables. We say that a function is locally linear near a point if the graph looks like a plane near that point. And there are examples similar to the absolute value function that fail to be locally linear functions of two variables. The book goes on to discuss some theorems about when functions are locally linear. There's a theorem that says that for single variable functions, if the derivative of a function exists at a point, then the function is locally linear at that point. But the theorem does not extend to multivariable calculus. Knowing that the partial derivatives exist at a point turns out to be insufficient to know that the function is locally linear. And you don't even need to come up with a crazy example. The function x to the 1/3, y to the 1/3 has both partial derivatives existing at 0, but the function is not locally linear there. The purpose of all of this is to remind you that there's another level of ideas and complexity to calculus that goes beyond just the computations. We're only scratching the surface of some of these high-level concepts. The work that we're going to do uses the following theorem. Theorem: if f of xy has continuous first-order partial derivatives, then the equation of the plane tangent to the graph of f at the point x0, y0, f of x0, y0 is this equation. When the function is locally linear, this tangent plane can be used to approximate the function near the point x0, y0. We can also turn this around. If we are given the tangent plane of f at x0, y0, then we can use this to read off the values of the partial derivatives of f at x0, y0. It doesn't even need to be in exactly the tangent plane form, as the partial derivatives are the coefficients of x and y. The other terms are just constants that have been rearranged and simplified. Students sometimes get confused by this because they try to match up the equations too literally. The manipulations to undo the step of combining the constants is not hard, but it's also not that important, so we're not going to elaborate on it. Linearization is an important calculus concept. It's part of a larger topic of finding different ways to approximate complicated functions by using simpler functions. You might remember learning about Taylor series expansions in single variable calculus, which allows us to approximate functions using only polynomials. Linearization is a simple example of this. If we graph a smooth curve and its linearization and then zoom in close to the point of tangency, we can see that there's only a small difference between the curve and the tangent line. We want to mimic this idea, but using a surface and the tangent plane. Remember that the goal is to get a good approximation of the function. It's important to compare the formula for the tangent line and the tangent plane because there are a number of important parallels. Notice that they both evaluate the function at the tangent point. This term plays the role of anchoring the approximation of the function. Then we have a derivative term multiplied by a difference term. We also see that the derivative term is evaluated at the point of tangency, and that the variable of the derivative corresponds to the variable in the difference. The derivative term gives us the slope of the function in a specific direction, and the whole term can be thought of as a change of the function due to moving in that particular direction. Although we won't do it here, we can expand this idea and use the second-order derivatives to get a better approximation for the function, just as we can use higher-order derivatives to get more terms in the single-variable Taylor series. This gets more complicated because we have many types of the higher-order derivatives, but it's not so complicated that you won't be able to understand the basics of it on your own with just a little bit of thinking. In the next video, we're going to take a look at differentials.